بسم الله والصلاة والسلام على رسول الله. So we were talking about Windows file systems, and we mentioned that within Windows file systems there are many file systems such as FAT, which is file allocation table, NTFS, which stands for new technology file systems, and resilient file systems. So during an NTFS, this is a very recap starting from last lecture. Within an NTFS, there is a master file table, and within this master file table, there is first 15 record, which is around 16 records is utilized for the system, and the rest for the user. So we have here seen like this is all the thing in blue is for the systems, and the rest is like for the user. So we mentioned also that the first record in the MFT is called MFT record. And we have also MFT mirror, log file, etc. We stopped last time till this part. We mentioned that this is an example of MFT record, and usually any MFT record starts with an identifier. This identifier can be file 0 or it can be other identifiers such as bad or zeros. So if I see something here like 49, 46, 49, 40C, 45, 30, this means that this is file 0, and this means that this is a correct normal file. If I see, for example, 00000000, this means that this is deleted file. If I see something else corresponding to BAAD, this means that this is actually a corrupted, bad file. So within this MFT, we reached like that within each MFT record, there are several attributes. Attribute 10, attribute 20, 30, and attribute 80. We mentioned also within attribute 80, we we count for 3 bytes, then we will find the size of the attribute 80 record, and then we will after 2 bytes we'll find 1 byte related to the residency of the data. So we know that within this MFT there is a file here, and this file is normal file, and the data related to this file is actually the size of the data is 4800. This is in big Endian, so I have to convert it to little Endian, and then I have to change it from hexa to decimal in order to know how many bytes is actually related to this data. So it is 4800. In order to change it from big Endian to little Endian, I have to swap each byte. So this is the first byte. I have to this is the byte to the right. I have to bring it to the left, and to the left I have to bring it to the right. It will be 0048. Then I have to multiply this to 16 by 16 to the power of 0. This is 16 to the power of 1. So the result will be 72 bytes. What does that mean? This means that attribute 80, the length of attribute 80 is 72 bytes. So, which means that this is the first byte, second byte, third, fourth, fifth, sixth, seven, until I reach 72. Once I reach 72, this means this is the end of attribute 80. And we mentioned examples of data run. We said that normally it starts with 21 or 22, but this is not fixed. This is the common, but this is not fixed. There is a formula to find the first data run. And usually the data run does not start with 00 or 0x or 1 or x0. So this means that if I see, for example, here 00, this is not a data run. 00, this is not a first component of data run. Those are not component of data run. This could be a potential component of data run, but it wouldn't be, because there is a formula we will follow, and from this formula we will be able to understand the first data run. Anyways, if I have this data run, like if you are given that this is the start of data run, this means that it has 2 bytes will be allocated to the number of clusters associated to the Ciceron, which is EE00, and this is the 2 is actually the first the offset of the first cluster of this data run. So we can decompose this in the upcoming example. This is just a generic example of an MFT record. Now let's take each component and decompose each component of the MFT record. We mentioned previously that each MFT record actually consists of several things, consists of like generic information, consists of more information, consists of attribute 30 related to the file name, consists of attribute 80 related to the data. So not only this, but also there is something before all of them, which is the called MFT header. So we know that the attribute of FMT consists of 10, 20, 30, etc., and also the MFT header. This is an important, actually, part of the MFT. So let's go to the MFT header. For all MFT records, the record field of interest are as follows. So if I have any header, usually a header has something called identifier. And this identifier means either if it is file or file 0, this means that this is a normal, clean, correct file. If the record identifier is 4 bytes of 0, this means that this is a file that has been deleted. If the file identifier is actually, for example, if it is BAAD, this means that this file is actually corrupted, not a correct file. So we have 3 identifier, either bad or file or 4 bytes of zeros. Okay. So we have something called record identifier. Let's look at this file identifier or record identifier. So this is a small chunk of an MFT. The first chunk, usually the MFT header. This is the first chunk. Now, the first thing is actually the MFT record header. And the MFT record header is actually the 4th or the 5th byte of the MFT, and this means file 0. This means that this is normal file. After this, so where is it located? This is located actually in offset 0, 0, 0 till 0, 4. So from 0, 0 till 0, 4 is actually, this is the offset of the file identifier. Now we have another thing. We have another thing called the number of bytes of, so this is number of bytes of FMT header. What does that mean? Now I know that within a file, there is a header and then the attribute. The header itself is actually consists of 32 big endian. What does that mean? I have to change this 38 big endian into little endian, which will be the same because we are talking about 1 bytes. So it will be 38 in big endian and 38 in little endian. And then I have to multiply actually 8 with 16 to the power of 0 and 3 to the 16 to the power of 1. And this will result in 56 bytes. This means that the whole header is actually 56 bytes, which means this is 16 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16, I have to, so 16 and then, so I have 16. Then I will count another 16. It will be actually 32. And then I will count another 16. It will be, this is 48, 48, 49, 50, 51, 52, 53, 54, 55, 56. So this is the end actually of the header. This is the end of the header. After the header, I will see the other attributes. So what we can see here, we can see here that this is attribute 10. So number of bytes of FMT record is 38. So 38 means 56 bytes. And I have to count 56 bytes till I reach the end. After this, I will see the first attribute, which is an attribute. Okay. After this, after the MFT header, I would like to know what is the whole MFT. What is the whole actually what is the whole MFT record? What is the whole MFT record? The whole MFT record means the header itself, as well as all attributes, with all attribute 10, attribute 20, attribute 30, till attribute 8. So this is the MFT record, which includes the header as well as all the attributes. So actually, after this, so I have to count for like kind of 7 bytes. So 1, 2, 3, 4, 5, 6, 7. Then I will take 4 bytes. This 4 byte is actually the size of the whole of the FT record, and this is larger than this for sure. This is the header, but this is the header as well as the other. So how can I calculate this? This is the big endian. I have to change this big endian into little endian. So it will be from 00040000, it will be like 00. It will be 00, then 00, then 04, then 00. So I have converted this from big endian into little endian, and then I have to change it from little endian into decimal. So in order to change it to decimal, I have to multiply this as to the 16 by 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. So it will be at the end 1024 bytes. This means that the whole MFT actually consists of 1024 bytes. After 1024 bytes, I will be able to see another file, different file with its information. So underneath this number under this number of bytes for MFT record, exactly I will see the MFT record number, because I might have 10,000 file or 20,000 file. So each MFT record has a number. So what is this number? So the last thing is record number. As you, for example, in university, you have, for example, an ID. This is the ID of the MFT record. So this is 440000, which will be changed to actually from big endian to little endian. It will be actually 00000044. So this 44 will be actually, so it will be like this. So it will be actually 00, then 000044. And this one, I will multiply it to the 16 by 16 to the power of 0, and this is 16 to the power of 1. Then it will give me the record number, and the record number is actually 68. So this is file. The sequence of this file, or the file record number, is actually 68. This means I have like other files rather than this file. So now each one has something called offset. So let's go back. Let's go back here. So the file identifier usually located in offset 00. The size of FFT record usually located in offset 1C to 1F. What does that mean? 1C to 1F. So this is 1, and this is C till 1F. Usually we will take, this is the offset, this is the address, but the last digit of this address will be the one on the right. So in order to identify the addresses, so how do I know the address of the MFT record? I will say the address is 0001101. Then I will consider here C till F. So from 1C till 1F. From 1C till 1F. What is the offset of MFT record? I will say, okay, 20C till 20F. So from 20C till 20F is actually 20C till 20F is actually the MFT record. Also, how do I know the number of bytes of MFT header? It will be 1, 4, 1, 4. And 1, 4, this byte is actually number of bytes for MFT header. So 1, 4 is the length of the header. This is the normal thing. So now I will show you an example here. I will access, there is a tool called HexEdit. And HexEdit, I can open any file. I extracted it from FTK tools, any physical acquisition of a drive. So let's say I will open this file. I have here multiple file. I have this. So as you can see, this is an NTFS. But where are these MFT record? In order to find these, it's very large, it's very long. It's very large and very long because this is actually contains a lot of information. And in order to know these MFT, I have to search. So I will say search, and then I would like to search for file. Maybe I will see something related to the file. Yes, excellent. This is a file. This means that this is an actual file, and it is normal file. After this, I will go to this. This means what? This means the size of the MFT header. And after 7 bytes, I will find the size of the MFT record. So 1, 2, 3, 4, 5, 6, 7. So this is the size of the MFT record, and this is actually the number of the MFT record. So the numbers actually from Big Indian, I have to change it to Little Indian. Is this the only file exists in the hard disk drive? No, we have another file. So as you can see here, the highlighted things. So whenever I press enter, so I might have large number of files. As you can see, the normal thing is that any file located in 0, I will call this and this offset. So it will exist in 7, 1 till 7, 2. Actually, the offset is not shown. But anyways, you can just understand that this is the files. Okay. Now let's go back to this. Usually, whenever you see this, you will see underneath it the number of bytes, then you will count 7 bytes, then you will see the number of bytes of the MFT record, and underneath it is the MFT record number. Okay. Now I will go to this. So this is a decoder where I can like fit all the information and it can like decode this information. So when if I have file 0, this means if I have this hexa, this is a normal file, active MFT record. If I see 42, 41, 41, 44, this means corrupted record. If I see 4 bytes of 0, this is a deleted or unallocated record. So when I run it, I will see that, okay, yeah, this is the same example as this in the slide. This is the same example as this. The same example, I just fed it to a Python in order to like decode the information. So it says that the signature in hexa is 46, 49, 40C, 45. This means that this is file 0, and file 0 means valid NTFS MFT signature, because if I see file or file 0, this means that it is a valid file. Regarding the MFT header, the size of the MFT header is 38 and 38 in hexa. So it is from big endian to little endian to decimal, it will be 56. This means the size in bytes of the MFT, of the fixed MFT header of the or the offset of the first attribute is actually 56. So I will count 56 for the header, then I will find the first attribute, which is attribute 10. Number of bytes for MFT record is actually this, as you can see here, 00040000. So it will be this is from big endian. I will convert it to little endian, and it will be in decimal 1024. This means that the full MFT record size is like 1024. Now, the MFT record number is 44000000, which means this is 68 in decimal. This is the record this is the identifier which record this is within the MFT table, because I might have like thousands of files. So which file I'm talking about? I'm talking about file number 68. So this is the general information about the file. This is the general information. Whenever you find file, okay, whenever you find any file, or whenever you find this identifier, you will go to the fifth one underneath it. You'll find the number of bytes, and then you will count for 7. Then you will find the number of bytes for MFT record, and then underneath that, you will find the MFT record number. This is the generic one. Let's go to this example. This is the generic one. This is whenever I see file in the beginning. Whenever I see file in the early beginning, but sometimes I might find file in the other half, not in the first half. So this is the file in the first half, but sometimes I might find file and yes, like this previous example. Let's go to this previous example. Let's go to the beginning. Type file 0. Yes, file 0. So this is an example where I find file 0 is in the other half. This is not common, but if you see it in this way, so we will like underneath it is actually the size of the MFT record or the MFT header. This is the size of the MFT header. Then you will count 7 bytes, 1, 2, 3, 4, 5, 6, 7, 8. Then you will take 4 bytes. Here, 1, 2, 3, 4, 5, 7, 4, 5, 6, 7. Then you will take this 4 bytes. This 4 bytes is actually the size of the MFT record. And underneath it is the size, is the MFT record sequence or number. Okay, let's go to another one, this one. So underneath it is the size of the MFT header. Then I will count 7, 1, 2, 3, 4, 5, 6, 7. Then after 7 bytes, I will find 4 bytes. These 4 bytes are actually the size of the MFT record, and underneath it is the sequence or the record number. So again, this is another example, file 0. This is the size of the MFT header, and 1, 2, 3, 4, 5, 6, 7. Then after 7 bytes, I will find the size of the MFT record, and this is the sequence of this file, and so forth. I hope this is clear right now. Now let's go after the MFT header, and from this, we will count, like we know that the header is just 56. So the header is just 56, and this is 56 into from here. So this is 10. This is attribute 10. What is attribute 10? Attribute 10 is actually the standard information about the file. So let's go to the standard information about the file. This is standard information about the file. What we can find here. So usually we'll find here, as I will show you. So we will find here, so I'll find 10, then I will like ignore 3 bytes. Then I will find the size of the attribute 10, size of attribute 10. So 60 in big Endian, if I change it to little Endian, it will be from 6000, it will be 0060, and then I have to, I have actually to change it to decimal, and then it will give me number of attribute for size 10. So if I get this, so for example, so it is 00, it is 60. This is in a big Endian. If it is in little Endian, I will have it 0060, and I have to multiply this to the 16 of power of 0, and this to the 16 to the power of 1. So 6 multiplied by 16, it will be actually 96 bytes. What does that mean? This means that the size of the attribute 10 is 96. What does that mean? So here I have to count for like 96, 1, 2, 3, 4, 5, 6, 7, 8. This is 8. 8 plus 16, it will be 24. And plus 16, it will be 40. Plus 16, it will be 56. Plus 16, it will be 72. This is 72. Plus 16, it will be 88. This is 88. 88, this is 89. This is 90, 91, 92, 93, 94, 95, 96. So this is still 96. After that, I will find the second attribute. The second attribute is 30. Sometimes we find 20, but if it is not there, this means that, okay, this is the second attribute. So after this, we'll find attribute 30. Okay, so yeah, so we'll find this is actually the, let's go back. So this is the attribute identifier, attribute 10. We will ignore 3 bytes, then we'll find the size. Then after that, we will count actually we will count for 18. So after this this is after we do know the size, we will count for 18 bytes. 18 bytes. If I count for 18 bytes, I will find several things in consecutive. So I will count for 18 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. After 18, I will find 4 consecutive 8 bytes. What are these 4 consecutive? So I will count 18, 1, 2 till 18. Then I will find 4 consecutive actually 8 bytes. What are these? The first one is the file creation, and then the file modification, last access, and the update date and time, because each file can be actually created, updated, modified, etc. So this is actually the date and time, but it isn't Hexa. How do I know the date and time? It actually requires a lot of enhancement, a lot of like changes, a lot of efforts in order to get from Hexa to date and time. So if I take the same snapshot and feed it to the Python, and I said, okay, I have in the standard information that actually the file creation date and time. This is the file creation date and time. This is the file creation data time. Start 2501 CE FC2A C9D801. So I will find it here. This is the file creation. So what does that mean actually in date and time? Because we need actually a date and time. So it says that this is the big endian, this is the little endian, this is the decimal value. We do know how to convert it to decimal values, but after that, it will give us a value in nanoseconds. And this nanosecond and actually should be transformed into a date and time. So it will be, this file is created on 15th of September in 2022 at actually 47 seconds, which means at 5 p.m. at 45 minutes and 47 seconds. So the file was created at this time. Also, we have another information, the file modification, the file last access. So we can also check the file last access. This is the file last access. I will feed it here and then run it from from big endian to little endian. So it will tell me that actually the file, so the file creation is at this time, but the file last access is the same date, as you can see here, the same date, but it was created at 5 p.m. at 45 minutes. But here, last access at 5 p.m., 54 minutes, which is like it was created and after 9 minutes, it has been accessed again. So this information is very useful in forensics to understand when the file was created, accessed, modified, updated, etc. Okay, so the first attribute is attribute 10, which is the standard information about the file. It gives us like, it starts with 10, then we will ignore 3 bytes, then we will find the size, which consists of 2 bytes, then we will count for 18 bytes, then we will see 8 byte for the creation, 8 byte for modification, 8 byte for last access, and 8 byte for the update date and time. Now we expect now to see attribute 30. So let's go to attribute 30. This is attribute 30. What does attribute 30 contains? Attribute 30 contains actually what? Contains the following. It starts with 30. Then I will ignore 3 bytes. And then I will see 2 bytes. These 2 bytes are actually the size of attribute 80. So if I have here 7000, this is in big endian. I have to change it to little endian. It will be from 00. It will be from 7000. It will be 00. Actually, this one. Then 70. Then I have to multiply this to 16 of power of 0. And this is 7 by 16 to the power of 1, it will be 112. So I have to have actually 112 bytes. So 112 bytes is actually allocated for attribute 30. And what does that mean? This means that, here's 1, 2, 3, 4, 5, 6, 7, 8. Usually this is usually 16. So this is 16. Okay, this is 8 bytes and this is 8 bytes. So here is actually 8 byte and I will add to this. So here's 8 bytes because we start from here. And 8 plus 16, it will be 24. And 24 plus 16, it will be 40. And 40 plus 16, it will be 56. And 56 plus 16, it will be 72. 72 plus 16, it will be 88. And 88 plus actually 16, it will be 1004. So this is actually, so this is 104, 105, 106, 107, 108, 10. So 4 5 6 7 8 9 10. So 110, 110, 111, 112. So we stop till here. So this is the whole size of 30. After this, I will find another one. As you can see here, what we found here actually what? We found 40. So this is the second one. So actually, I will not tell you, I just need actually the size. I will not tell you to count. You usually see, okay, 13, usually, you will count 112, then you will find this, the second attribute, which is here 40. So what we find an attribute in the file name? In the file name, I will know the size of the file name. Then after that, I need actually to count for so usually this is the this is 30, attribute 30. After 3 bytes, I will see the size. And after actually 18 bytes, I will see the file creation, the file modification, the file update, and the last access. So I will count now actually 20, I will count actually 1, 2, 3, 16. So this is 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So I will count to 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 20, 21, 22, 23, 24, 25, 26. And then I will start to see the first, I will see 4 consecutive 8 bytes of file creation, then modification, then last access, then the update. Actually, the sequence is as it's, so we see the same sequence: creation, modification, last access, and update. This is the normal thing. So to make it simple, usually we do know that we do know that an attribute 80, an attribute 10, I will ignore the 3 bytes, and then I will see the size. And after this size, I will count for, after this size, I will count actually for 18 bytes. If I count for 18 bytes, then I will see actually the creation, modification, last access, and the update. Here, I will see the size. But in order to get the creation, modification, etc., I have to count for 26 bytes. After 26 bytes from the size, I will see the creation, modification, last access, and the update. And because we are talking about file name, I should have something related to the file itself. So this is the file name. So this is the file name, and the file name is actually, because it is written in English, you can see some hints here, galaxy.gif, but sometimes if it's written in Arabic, you will not see the example here. But this is the file name, and I have to change this from actually hexa to ASCII in order to understand the file name. So if I fit this to my Python and said, okay, the file creation date and time, this is the file creation date and time. This is the creation. So this is the creation data time. And the file last access, it will be here. And the file name, so I will give the file name. So it will be, this is actually galaxy.gif. But if I have another hexa, let's say this is another hexa example, I will see something .exam.docx. So it varies, like it depends on the values here. It will show me the file name. Okay, now we have covered, we do know that for each file, we have file header, we have attribute 10, which is the standard information. We have attribute 20, which is more information. We have attribute 30, which is the file name. And the most importantly is attribute 80, which is the data. So let's go. Yeah, here's just an example of how we convert these things. Okay, so here's attribute 80. Attribute 80, again, the same thing. We will see here attribute 80, and then I will ignore 3 bytes. Then I will find the size. Size is actually 2 bytes. So it is actually 7801. I have to convert it from big Indian to little Indian. It will be actually 0178. So I have to convert this into decimal. I will multiply this to 16 of power of 0, 16 to the power of 1, 16 to the power of 2. It will give me 376 bytes of the whole thing. So I have to count 376 till I reach the end of the till I reach the end of the attribute 80. So after that, I have to see attribute 90, etc. So after this, I have to ignore 2 bytes, and then I have to see something called the residency flag. Residency flag, it will be either 00 or 01. 00 means the data is resident, which means I see it here. 01 means that the data is not resident, so I will not see it here. So if I see 01, means the data should be outside the MFT record. So this is 00, therefore the data, you can see the data here. But if it is 01, you will not be able to see some data here. Usually, yeah. Now, this is actually, this line means the sector boundaries. So this is a sector and this is a different sector. And at the end of each sector, like the last 2 bytes in each sector, or sometimes the last 4 bytes in each sector contains the sector checksum, which ensures the accuracy and the correctness of each sector. Okay. Now, here is another example of attribute 80. So here's attribute 80. I will ignore 3 bytes, and then I will see the size 6000, which means 96 bytes. What does that mean? Attribute 80 has 96 bytes. So this means that here is actually, if I count it here, I will see here. Okay, so the first one is actually, this is 16. And this is actually another 16, so it will be 32 plus 16, it will be 48. 48 plus 16, it will be actually 46. 46 plus 16, it will be 80. 80 plus 16, 80 plus 16, it will be 96. So here is actually the end of this is the end of the of attribute 80, because this is actually 96. So actually 96 is actually kind of 6 rows. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it will be here actually, here. So this is the end, because this is the end of 96. Okay, so now after we get to know the size, we will ignore 2 bytes, and then we will see the residency flag. The residency flag is actually 01. 01 means that the data is actually not resident, not exist here, but we can see something else called data runs. So these data runs is actually kind of several components. Each component consists of 3 components. I will explain this in upcoming slides, in this slide. Yeah. Let's say that this is a data run, any data run. Like, let's say that this is starting point of data run. What does that mean? This means any data run, the first component is number of bytes. So here you can see number 1. This means I will take 1 byte only, and this 1 byte only consists of number of clusters allocated for this data run. So this is the number of a cluster allocated for this data run. Another thing is actually 2. 2 means number of bytes needed to understand the starting cluster address of the file. So I need to take here actually 2. And then I have to convert number of clusters, 1B from the big endian to little endian to 1B, and then 1B I have to multiply B to 16 to the power of 0, and this is 16 to the power 1, then it will give me number of clusters allocated. So this is another example. So if I have such an example, 2106, so if I have this example, 2106 56 FA. So what does here 21? 1 means, what does 1 mean? One here means number of clusters allocated for this data run. So number of clusters allocated is just 1 byte. This is 1 byte. What does 2 mean? 2 means is the address of the first data run. So here is actually, so 2 means I have to take one byte and another byte. So here, this one means number of clusters associated with this data run. So it is 0, 6. 0, 6, actually this is in a big endian and little endian. So big endian is actually 0, 6, and little endian, it is 0, 6 as well. So 2 decimal, it will be 0 multiplied by 16 to the power of 1 plus 6 multiplied to 16 to the power of 1. This means what? Power of 0. This means actually 6. So 6, what does that mean? We need 6 clusters. So this data run requires 6 clusters actually. 6 clusters. Okay. Now this 6 clusters, in order to know, so I have to have 6 clusters for this data run. 1, 2, 3, 4, 5, 6. 6 clusters. And the address, so this is 6 clusters. And the address of this cluster, is actually 56FA. So the address of the first cluster is actually this one. So this 2 means 56F1. So I know you need actually 6 clusters. This is the first cluster. This is the second. This is the first cluster. 1, 2, 3, 4, 5, 6. And the address of the first cluster is 56FA. 56FA. This is the meaning of each data run. Let's go back to this example. Let's go back to this example. Now, how do I know the first data run? Understanding the first data run is actually requires some calculation, some formula. We do know that it is usually start with a 21 or 22, but this is not normal. This is a common, but this is not always to start with 21 or 22. Okay, so in order to know the first starting data run, there is a formula. It's not required. It's not exist in the textbook, and it's not even asked in the midterm or the final, but it is for you to learn. So how can we calculate the first data run? In order to understand how can we calculate the first data run, the first data run is actually the offset of attribute 80 plus little endian value of offset of attribute 80 plus 20. What does that mean? Now, I would like to know what is the first data run here. So I do know this is 80. I do know this is the size. I do know that this is residential flag. But where's the first data run? I will keep the same formula. Now, the formula, the first data run, tell me the offset of attribute 80. Now, where's attribute 80? This is attribute 80. What's the offset of it? The offset is here. But actually, I will ignore the first one. I will consider this one. So, this means that the offset is actually 0, 0, 0, 1, 1, 1, 3. But actually, all of this, the first digit will be taken from the column. So the offset will be taken from the rows, but the last digit and the offset will be taken from the column. So this is 0, 0, 0, 1, 1, 1, 3, and then here 0, 0, which means 0. So the offset of attribute 80 here located in this offset. Now, I will take little endian value at. I will keep it as it is, little endian value at. What is the offset of attribute 80? The offset of attribute 80, again, the same thing. It is this one. I will take the rows, and the last digit will be taken from the column, which is the same thing as here. And I will add to it 20. So I will add to it actually 20. Okay, what does that mean? I will keep the same thing plus little endian value at. So if I add this value to this value, it will be 0, 0, 0, 1, 1, 1, 30 plus 20, it will be 70. Now I need to go to this offset and I need to see the value of it. So this one will be as it is. And I need to go to this and see the value of it. So where is this offset actually? 0, 0, 0, 1, 1, 1, 70. This one. Okay. This one, 70. Sorry, it is 50 actually. 30 plus 20 is 50. So it will be this one here. So the value of this offset, 11150, is actually 40. So 0, I will take the same row, and the column is actually 0. So it will be 0, 0, 0, 11150. It will be 40. So it will be actually 40. Because this is the one actually here. This is it. It will be actually here. So I will take it without the last one. So I will take it like this. And here I will take the actual, so the offset 0, 0, 0, 1, 1, 1, 5, 0 is actually, the value of it is actually what is 40. This is the 40. So I will take here 40. This is the 40. So now I will add 40 to 30. It will be 0, 0, 0, 1, 1, 1. 30 plus 40 will be 70. So the first data run is actually at this offset. Where's this offset? This offset is actually here. Here. So 111170. So this is the first data run. This is the first data run. And then from this first data run, I will be able to calculate, okay, this is 2, 1. This means I need 1 byte for number of clusters required for this data run, and 2 byte as the address of this, the address of the first cluster of this data run. Then I have another data run, 1, 1. 1, 1 means I need 1 byte for number of clusters required for this data run, and 1 is actually number, and the 1 is the first address or the address of the first cluster of this data run. And this 21. 21 means I need 1 byte for the number of clusters for this data run, and 2 is number of bytes, the address. So the address of the first cluster of this data run, and so forth. We might have multiple actually data runs. So till we reach here. If I reach here, I find here 0, 0. 0, 0 means this is like it doesn't make sense. I should not have a component with 0, 0 or 1, 0 or 0, 1 as a first component in data run. So خلاص, this is the end of the data run. If I take another example of how can I find the first data run, I might go to this example. So I will say, okay, so how do I know the first data run? I will say, what is the offset of attribute 80? The offset of attribute 80 is actually, 0, 0, 9, 0, 0, 9, 0, 0. E 9, 0, 0, this one. So 80 is actually located in E90, but actually, let me take this. So this is 80. So I need to take the row, which is 0, 0, 0, 0, E90, okay? Without the last digit will be taken from here, 8. So it will be 9, 8. Here is 4 zeros. I can write it like this, or I can write it in another way, which is 0. I can write it 0x E908. This means that whatever, and yani, all the previous numbers actually zeros. So if I write it this way, this means zeros and then E908. The same thing. They are the same. So now offset of attribute 80 is actually 0xe908 plus the little Indian value at, what's the offset of attribute 80? This is the offset of attribute 80 plus 0x20. It will be the same. Now, and plus, so so I need to go to this 0xe908 plus a 20, it will be 28. I need to go to this 28 here. So where's 28? 928. 928 is actually 928. Where is 928? Here, 92. Here's 92. So here's 92, and here is 8. So here is 928, which is the value of it is actually 40. The value of it is actually 40. So E928, the offset is actually, the value of this offset is 40. So it will be like this. Which means 0xe948. I think this is the value. Or this is the offset. So this is the offset of the first data run. So I need, in order to get this, the offset of first data run, I should go to 948. So 948. Where's 948? So here is 94. It is 94. And I have to go to 8. Here is 8. So this is the first data run. And then I can count the first component, second component, and so forth. I hope this answers how can I find the first data run. Usually it starts 21, 22, but this is not always. There is a formula to find the first data run. Now, let's go back to the lecture. So okay, so again, in any MFT, we can find a lot of files. Each file has features. It has header, standard information, which is attribute 10, attribute 20, 30, 40 till 80. And for each attribute, there's a size and there are further information. You should know how can we find this further information. So just to simplify it, here's an example of this file. So I can see that I can also open another one. So this is another example, which is like partition 2. I would like, as you can see, it starts with NTFS. So within NTFS, I can search for files. So here's file, but within this file, I will see a lot of information. I might see, for example, attribute 10, attribute 20, attribute 30, attribute actually 80. So we might find something like this here. As you can see, here's attribute 30. After 2 bytes, we find the size, and after after like several things, we can file creation, file deletion, file creation, file modification, updates, etc. Then this is like, and so forth, like, and yeah, till we go to the second file, which is the second file is here. So this is the second file. So all of the previous one is related to that file. And then the second file, we had to find another thing, and so forth. Also, if I go to take another partition, I might find the same thing, 0. So this is NTFS, but there are a lot of files here, as you can see. Okay, now we will talk about alternate data streams. What is alternate data streams? Alternate data streams actually a feature in NTFS. And within this feature, we can add files to files. So like sometimes we can add files to files, we can add image to file, text to file, a way to hide information within another file. So I will show you here in this example. Yes, these alternate data streams. So imagine that within alternate data stream, this file is actually normal file. It is visible to user. It's shown to user, but I can add data called streams to this file. So this stream can be actually a text. It can be a video. It can be a picture. It can be whatever. This is a stream. This stream can be hidden, and it is not shown to user, but it is visible to the file systems only. I can add two actually, like within this file, I can add a hidden image and a hidden video. And those things are not shown to Nucleo users. It will be only shown to the system. So in alternate data stream, usually I have to have a primary file, which is here, as you can see here, file 1, and streams. Streams, this the default stream is the actual data. It's visible to everyone, but the other hidden stream is actually not shown to anyone. And there are some key facts about alternate data stream. If the primary file is deleted, so if I delete file 1, all the streams actually will be deleted. Another fact, there is no built-in feature in Windows to detect the alternate data stream. So it requires some efforts to detect the alternate data stream. And the primary files could be actually Word, text, image, video, audio, PDF, executables, even the alternate data streams, it can be whatever. So this primary file can be audio, video, text, and even the alternate data stream, it can be video, audio, text, and whatever. More than one hidden alternate data stream file can be attached to the primary file. I can attach multiple data stream, 1, 2, 3, etc., to one primary file. So how can we do this? So alternate data stream is ways that data can be appended to existing file and can obscure valuable evidentiary data intentionally or by coincidence. And NTFS and alternate data streams becomes an additional file attribute. It allows the file to be associated with different applications. You can then tell whether a file has a data stream attached by examining the MFT entry. How can we do this manually? I will show you. I will show you here. So if I have Callie and then here Callie. Okay, so clear. So let's take this example. So I can say, for example, now I would like to go to the desktop. So CD, desktop, and then there are several files I would like, for example, to create. So I would like to create a file called, for example, a game, let's say. So I will say echo. This game is about etc. Game is fun and requires 2 players, etc. So then I will save this into game.txt. So this is a regular file called game.txt. I will see here game.txt. So if I open it, this is the file. Now, how can I append extra files to this? I will type echo the password to open the password, for example, is A6 $3, or let's say RESQ to open the exam document, let's say. And then I will save this into game.txt. And then I will add colon, then secret. Then I will hit enter. Now, if I open, oh, okay, it shouldn't open, it shouldn't create this one actually. I will type no, it shouldn't actually create any file here. It shouldn't create any file. So I will try to generate a new one. I will type echo then I will type echo secret or hidden. Then if I type now cat dot test 11.txt, this is a visible text. But if I type hidden, it should show me this is the hidden text. So this is a way to append further information to this file, and it shouldn't be shown to the regular user. Actually, this is actually related to the NTFS file system. So if I deal with it in Windows, it would be easy to do it. If I do it in Kali, I have first of all to actually create a storage medium with NTFS file systems, then I can do this. So this would be better way to deal with it. Okay. So alternate data streams within NTFS allow embedding metadata and files or folders without altering their original functionality or content. And NTFS, the main data stream, refer to the standard content of the file or folder, and this is usually visible to the user, while the alternate data stream is not shown to the user, it's hidden, and like only the user who created it can find it, or using specific tool you can actually extract these information. Some of these benefits include, like, what are the advantages and disadvantages, or what are the good intention of using alternate data stream and one of the bad intention of using alternate data stream. One of the good things of using alternate data stream is that, for example, you can hide some information, some keywords, some summaries of information, some information related to the safety or security of the file, maintaining the integrity. But there are some bad intention of using alternative data streams, such as, for example, hiding some malwares, hiding some bad intentions, or some keywords utilized by hackers. So it is. This means that the usage of alternative data stream is not always bad. It can be utilized for good things and for bad things as well. So yeah, here we already talked about alternative data stream. And it runs. Now, one of the advantages of NTFS is that it enables the compression. So NTFS provides compression similar to the FAT, and we can use one of the utility called the driver space 3 to compress files. If I compress file, I will find the compression and non-compression feature in the attribute 80. But the point is that, like, NTFS enable compression. Under NTFS, files, folders, or entire volume can be compressed. Most computer forensics tool can uncompress and analyze compressed Windows data. Why? Because usually handling large number of data requires compression and uncompression to facilitate data transfer and data handling. Now, after we have covered the FAT file systems and NTFS, we will talk about a feature within NTFS called EFS. EFS means encryption file system. So encryption file systems, or encrypting file systems, actually was introduced since Windows 2000. And the idea of using an encryption, it means that it is utilized actually the public key encryption, which is the public key and the private key. So, for example, if I have this computer and this computer has 3 users, each user, like the file can be encrypted by the public key, but in order to decrypt this file, I should access with my username in order to decrypt the file with the private key. So the decryption will be based on the user login to the system. So for example, if I access the Windows using my account, then you take the private key and decrypt the whole files. This encryption and decryption can apply to files, folder, or disk volumes. Now, within an EFS, there's something called recovery certificate, and recovery certificate is actually a certificate generated and sent to the administrator account. So if, for example, any user lost his private key to decrypt the data, that recovery certificate can do the job and decrypt any encrypted files. So users can apply EFS to file storage on their local workstations or remote server as well. So now, as I mentioned, that there is a recovery certificate sent to the administrator. So the administrator is called recovery key agent. Why? Because he can decrypt whatever encrypted files. So Actually, Windows administrator can recover a key in two ways, either through a graphical user interface or through command user interface. Within command user interface, he can utilize, the administrator can use cipher copy or EFS recover. This EFS recover, like we can put any file or folder or partition and it will be decrypted. This is interesting if I have, for example, several user, for example, a user with name Ahoud. Okay, this is the first user. And if I have another user, his name is, for example, Noor. Okay, and if I have here, for sure, for all of them, we have the admin, and the admin can decrypt the admin because he has a certificate, recovery certificate. If any user forgets, like Ahoud encrypt all her files and Noor encrypt all her files. Now, once Noor accesses her account, all the files will be decrypted because she will provide the private key of the files. But what if Noor forget the user and the password of her account? We will go to the admin. The admin has a recovery certificate, and he will decrypt all the files of Noor so Noor can access all her files. Now, how can we delete a file in NTFS? So in fact, in order to delete any file, I will replace the first letter with actually E5. So if you do remember, going back to the FAT file system, if I delete any file, I will remove the first letter. I will remove the first letter with E5. So let's say that this file is actually, the name of this file is Moon, and I would like to delete it. In order to delete it, and I'm using FAT file systems, I will remove the first letter and I will replace it with E5. E5 means actually, E5 means like this. This is the E5. So it will be A-O-O-N. So this means that this file is actually deleted. But what about deleting a file in NTFS? Deleting a file in NTFS has two ways. If you deleted any file, if you deleted any file, I'll show you here. Yeah. If you delete any file and you let this file to the using, for example, if you delete any file and put it in the recycle bin, in this situation, the operating system will rename not only the first letter, but it will rename the whole file. It will rename the whole file and move it to the recycle bin, but it can be recoverable. It is easily recoverable. However, if we do a deletion, but in another way, by pressing delete keyword, delete keystroke. So if I press delete command, this means that I will eliminate the file from the master file table listing. So it will remove the whole file from the MFT file table, but the content will be existing. So it will be actually unallocated. So here are the difference. If I just take a file, so if I just take a file and put it to the trash, the file will be renamed and it can be recovered easily. But if I press delete, the delete will not rename it, but it will remove the whole thing from the MFT. But it will remove the name of the file from the MFT, but the data will be exist actually, especially if it is non-resident. So the data will be unallocated data. Now we'll talk about the resilient file system. The resilient file system exists usually in data where it requires like large number of users, where it requires further availability, integrity, and scalability. So therefore, we can find it in a lot of servers, such as starting from server 2012 till 2022 and 25. It enables the availability, enhancing availability and integrity and the scalability of files. So resilient file system uses disk structure similar to the MFT and NTFS. So in FAT, we have FAT allocation table, and NTFS, we have MFT table, and in resilient file systems, we have also a file table similar to the MFT. Now we'll talk about disk encryption. And disk encryption Sometimes our disk contains very important information, and we need to encrypt this disk. Actually, there is something called personal identity information. Personal identity information is that information that identify who you are. Okay. For example, I have a lot of files in my hard disk drive. Some of them are really important and actually identify who am I. Others are actually taken from the internet. So if anyone actually steal it, it's okay because I already downloaded from the internet. So our hard disk drive sometimes contain personal identity information such as our national ID, our passport information, etc., bank information, and sometimes other files that can be actually taken from the internet that's not secret actually. So we might have secret information, restricted information that if you have a file that's shared between your group and your project or your graduation project, and sometimes public information. The secret information or the information you don't want to share with others called personal identity information. And sometimes these disks also contains trade secret. A trade secret is like information exists in companies and they don't want to share it with other organizations. They call trade secret. So if this hard disk drive is stolen and it is not encrypted, this means that anyone who steals this device can find all the data, whether it's PII or trade secret. So in order to protect, we can utilize an encryption, disk encryption. So of particular concern is the theft of laptop computers and other handled devices. To help prevent loss of information, software vendors now provide whole disk encryption. So whole disk encryption provide the following features. Pre-boot authentication, what does that mean? Before booting, so once you power on the device, it will not boot unless you enter a password. This password will enable the boot and then decrypt the disk and view the disk. Why we have pre-boot authentication? To prevent anyone from manipulating the hard disk drive and to change the boot sequence and then access the hard disk drive. So it enabled the pre-boot authentication. So before actually booting the device, you will be asked for a password. It enabled full or partial disk encryption with secure hibernation. So I can encrypt the whole disk or a specific partition. And it enables secure hibernation. What does secure hibernation? Secure hibernation, sometimes the system is like in hybrid mode, hibernation mode. So the data actually exists in the RAM, so now I am opening multiple applications. For example, I'm opening Microsoft Teams, Zooms, Word, etc. Also, any password, like let's say now I'm typing here any password written here actually will be stored in the RAM, in the memory. So the memory contains information. So the secure hibernation means that we are going also to encrypt the data exists in the RAM. So this is the secure hibernation. Advanced encryption algorithm, the whole disk encryption support the advanced encryption algorithms such as an AES and key management function, because again, an encryption, every single user will, like, the data will be encrypted and it will be decrypted by the private key of the user. So the management of these keys will be actually considered in the whole disk encryption. And in order to do the whole disk encryption, we have to actually in whole disk encryption, each sector will be encrypted, and many of these tools encrypt the drive boot sector to prevent any effort to bypass the secured drive partition. So the same thing of actually pre-boot authentication. And pre-boot authentication, we are preventing any effort to bypass the secured drive partition by asking for the password once we powered on the device. To examine any encrypted drive, we need to decrypt it first. If we can't see the plain text, this means that the encryption went normally. So we can have actually some vendor specific programs such as BitLocker, and sometimes we can use third party to decrypt the data. or encrypt the data. So BitLocker is actually exists in Windows 7, 8, 11, and also in some Windows Server. So we can see here, if I go to BitLocker, BitLocker actually exists in some Windows Server, and there is a way to install BitLocker in Windows Server. Also, we can find that BitLocker exists in Windows 11 Home or in Windows 11 let's see this one. So if I go to Windows 11 and I would like to compare between them, so BitLocker Drive and encryption is actually not available in Windows 11 Home, but it's available in Windows 11 Pro. This means that, just to let you know that يعني, there are some editions in Windows that has a BitLocker feature exist. So it's available in Windows 7, 8, 11, and some Windows servers such as 12 and Windows Server 25. There are several hardware and software requirements to have BitLocker available in our devices. These are like what are the edition of the operating system that you are running. So you have to have Windows Vista or later. We have to have Trusted Platform Module. Trusted Platform Module is actually a hardware existing in the motherboard to facilitate the encryption and decryption. We have to have a BIOS as well as two an NTFS partition. One contains the one NTFS partition. So one contains the encryption, decryption information, and the other one for the system and the data, and a BIOS. So all of these things are like required software and hardware. And if we would like not to use the vendor specific application, which is the BitLocker for Windows, we can use third party such as BGP full disk encryption, Voltage Secure File, and many other encryption tools. So in this chapter, we just like mentioned that there are several file systems in Windows, FAT12, FAT16. These are oldest like file systems. We also introduced NTFS, and it has master file table, which has 16. The first 15 record as actually stored for the system, and the rest for the user. And also we talked about encryption file systems and resilient file systems and different way to encrypt and decrypt disk drives. That's all. I hope everything is clear. If you have any questions, you can ask me at any time. Thank you.